Alright, here's the second video. And I just finished the other one about 7 seconds ago, so it's kind of interesting how this works. I still can't find my big red marker, which kind of upsets me a little bit. And hopefully this is all coming out okay. So, how do we use diodes? There are two basic purposes for using a diode. Alright, one of them is directional control in a system or circuit, but mostly a system. And we can use it also for arc suppression in coils. So I'm going to do arc suppression first because I'm going to break my own rule about direction of current flow. So diodes for arc suppression, meaning when a coil discharges, coils produce voltage because they're a generator. There are three things you need to make a generator, okay, and this is called electromagnetic induction. Electromagnetic gotta spell this right, induction. And what that means is we're inducing or putting in a voltage through the use of electromagnetism. And there are three things we need. The first thing we need is a magnet. That's pretty obvious. The second thing we need is wire, usually in the form of a coil, not necessarily, but usually. And the third thing we need is motion. And you put these together in any form, you get voltage. Okay? And it makes sense that if we increase that, or we increase that, or we increase that, we get more of that. Pretty straightforward. So more of that, 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 more of that. Well, in the case of the coil, the motion is pretty much at the speed of light. It's quick, really, really, really fast. And there's usually quite a bit of wiring because we've got a coil of wire, right? So what happens is we take a coil of wire, all right, and let me draw this way. There's my coil of wire. And we get this magnetic field. I use green for fields because, you know, in the springtime when the snow melts, fields are green, right? Plus I have to have some reason to use some color other than black. So what happens is this field is built when current flows through the coil, but when current stops flowing through the coil, the field collapses very fast. And that collapsing, that arrow wasn't very good, was it? Okay, well, there we go. So this arrow and this arrow, whatever, there's the motion. So this field right here goes pew, really fast. Boom, snap. Well, there's your motion, and here's your wire, and there's your magnetism. So a coil, when a coil turns off, it's a one-shot generator. So the devices that we almost always deal with are solenoids and transformers. And we're not talking AC, but it's the exact same principle. So in the case of the world that we live in, the most common place where we're going to see this is going to be with a solenoid. And the solenoid, there's more yelling from the kids if you can hear it. It's snowing, so they're arguing about who's going to drive to go sledding and if they're going to go sledding and what's going on. So, all right, so here's a solenoid. Well, inside the solenoid is a coil of, what color should I use? I'll use orange. Is a coil of wire. Well, I'll use blue because I use blue up here. That's the first insistent. Okay, there we go. Okay, so, all right, so there's blue. Okay, so here's my coil. And there's my terminals. And that's why you can put a compass on here. Okay, that's why you can put a compass up here, if you remember watching that video. All right, and if this magnetic field is working, then this compass will point one way or another. And it'll tell you that the solenoid is magnetically functioning, which tells you that the electrical circuit is complete and it Saves you a lot of trouble and time, and it's a really good way to diagnose here. All right, so anyway, so there's your compass. Not a very good compass, but there's a compass. Okay. So I did have a red marker. Where did I lose my red marker? Doggone it. I need the red marker. Oh, found the red marker. So at any rate, right, so it'll pull north or south, whatever. Okay, a little bit, you know. So here's the deal. Here's the problem we have. If this coil is connected to a relay, put this up there. If this coil is connected to a relay, and if you remember what a relay is a set of contacts with a coil of wire in it. Now normally I'd use green for the coil, but I'm not going to do it. Okay, so I've got a relay, right? And the relay is a switch, right? So here's the problem. If this coil is powered by a relay or any type of switch, doesn't matter, or worse yet, if it's controlled by an ECM, all right, so that inside the ECM there's a switch of some kind, usually a transistor. There you go. The problem is now the arc that's going to be produced by this coil when it collapses is going to zap here. Right here, it's going to go zap, 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 zap. Oop, well, if I can make the stupid laser work. It's going to go zap, 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 zap. And every time that contact opens, not closes, opens, you're going to get about a 2500 volt spike. And if it's inside the ECM, that's bad. Okay? So you're going to get all this arcing that's going on in here, and this will spike things, and this will spike things. Okay? So that's bad. So what do we do? Well, we use a diode. Very simple. And this is the only time in my class that I can think of when I actually talk about or use direction of current flow, simply because it's convenient. Not because I believe it matters so much, but because it's convenient. So I'll draw a fuse, and I'll draw a switch. The switch will be closed, and I've got a dozen or more different symbols for a coil, so I'll use the one that's very common. And then I'll take the diode, and I'll put the diode, and this is important, the diode will always be in reverse bias. All right. So what do we got here? Well, we got a power, ground, load, and switch. That's the 4 elements of a circuit that will always be there. And in the case of a coil, it could even be a relay coil, it could be a solenoid, it could be any kind of coil at all. AC clutch, good example. This is the same circuit as an AC clutch, by the way. There's your solenoid, there's your AC clutch, there's your relay coil. That's the same circuit. We could draw it exactly the same way, and this could be 3 different things. Very important to remember that when you're doing schematics, okay? So, here's what happens. Well, and I will use positive flow because people like positive flow and it's easy to understand. So when I close this switch, then the electrons are going no, 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 whatever, the holes or electrons, I don't care. Zing, 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 and it's making this field right here, okay? So this coil, I won't draw it because it'll kind of make it a little confused. This field is being produced by this coil one way or another. I don't know which way. It could be this way. It could be that way. I don't care. But the current's going no, 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 no. We'll just call it current flow, positive flow. It doesn't matter. Okay. If you want to get involved in an argument about current flow and positive flow and conventional flow and negative flow and traditional flow and all that kind of stuff, it's an argument. That's all it is. It doesn't matter. It doesn't do. My daughter's back, so I'll have to stop the electrons here for a second. Hold on. Okay, now it's about sledding after 10 o'clock and I have to drive. So, okay. I love being a dad. I really do. It's, it's crazy, but it's good. Okay. Where was I? Oh, okay. So, electrons going zing, 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 whatever. Okay, but so if we use positive flow, that's fine. I don't care. There they go. But they can't do this. They stop, right? Because based upon what we know about diodes, current flow, blocks, whatever, so the currents turn this diode's in reverse bias, so it's off because positive is touching negative and negative is touching positive. It's backwards from what you'd think. Well, that's right. So what happens is the current goes through here, whatever noise current makes, and when it comes up here, it goes, and all the electrons go, big rear end collision there, and they stop. But then this magnetic field, when we open the switch, that magnetic field, boom, snap, crackle, pop, bam, really fast. Well, that produces a big-ass spike, okay? So that big-ass spike is about 2,500 volts, okay? So let me do this. Oh, there they are, scissors. Okay, do this, take that, put this here, and boom, we get rid of that. And now the switch is open. The magic of stickers. All right, so now we open the switch because we want this to stop doing whatever it was doing before we wanted it to stop. And so when it stops, that magnetic field has to go away. It can't just, it has to go away, right? So I think of it as like a bow and arrow, you know. Right, well, when you pull the bow back, you're cocking a spring, basically, and that's kind of like that. So, okay. And then that energy has to go somewhere. So you can either let go, and the arrow goes like that. I think that's the sound it makes. Or you can go and whichever, but the energy has to go. It either has to go back in your arm or it goes into the arrow. Okay. All right. So here's what happens. There's a little thing called Lenz's law. Okay, and you can remember it or not. I don't really care. But Lenz's law says that if this magnetic field here is built by current moving in this direction, for example, then when the field collapses, it will make a voltage that wants to keep current moving in the same direction, which it does. So this magnetic field is being built by current moving in this direction. So when the magnetic field collapses, it's going to produce a voltage that's going to want to make current go in that direction. Okay? So now let's look at this for a second. Watch what happens here. Laser pointer. There it is. Okay. So now, if you hear the dog's outside barking. We have a pain in the butt neighbor dog that taunts him. Okay. So now, this can't go anywhere. So this is a big open circuit, right? But this is not. Well, now, because this voltage is trying to make current come all the way back around here. There's no such thing as backfeed. And arc this way, which it will do. This could be 100 feet. I've seen it happen on a big-ass coal truck. 100 feet. Back into the truck, front end of the truck, arc, 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 every 2 weeks, new switch. Okay? So that's a good symptom for you to watch for. Every 2 weeks, you lose a switch, I would check the diode on the coil, assuming it's a coil. So, current can't go this way anymore, but this has got a big-ass charge of voltage that it needs to get rid of. So what it does is it collapses and goes and stays right here. It goes away. So instead of coming all the way back around here and going pow and blowing up that switch, which it will do, and I suggest you do an experiment using a starter relay or a big solenoid of some kind, I'll have you do it. Instead of doing that and coming, boom, blowing up here, it goes, and goes, zing, and goes away. Okay? That is that. That's why it's there. So what I tell people is, very simply, when you're reading a schematic, okay, when you're reading the schematic and you get a coil, and the coil has a diode attached to it, whatever you do, do not care about the diode. Don't worry about the diode. Okay? Because what I do is I treat all of this as one thing when I read the schematic. It's just a coil. Oh, and by the way, it has a diode. Well, that's important because this diode could cause that switch to fail if this diode fails, or this diode could short, causing that fuse to blow, so it's important to know it's there. No question that it's important to know it's there. But when you're reading the schematic, you don't care. Don't go, oh, well, then current does this and current goes here. That's not how I teach you to read schematics. I don't care which way current flows. Okay? We're drawing a straight line, and the diode's either going to point towards positive or towards negative, and you'll see when I do the second half, that's what's going on. Okay, so this is a suppression diode. What it does is it takes the 2500 volts or so, and for meter reading, I'm going to take, I'm going to say 2.5 kV. Instead of 2500, because I want you to know that 2.5 kV, that's 1,000 right there. 2.5 thousand is 2,500 or 2,500. This diode prevents this switch here from being destroyed. Okay? The important thing to understand is that this diode doesn't do a damn thing for any switches in this area. So if you've got a big, starter relay thingy mabobber, let's see, and you got this thing, and you got this thing, and you got it goes like this, and comes like this, and then you got this side, and it goes like this. It's not very clear, but you get the point. And then it goes right here. Okay, and inside here is a big old set of contacts. That's what's inside here. You got a big sort of, and then there's usually a washer. Okay, and then what happens is the solenoid, which is why people call it a solenoid, because there's literally a solenoid in there. Okay, but it's really a relay. When this gets pulled down, it closes those contacts. Okay, but, if there is a coil, I'm sorry, there will have to be a coil. That's kind of what it is. All right, so you've got the two little Dumahookie terminals out here, and then you've got the coil inside, and that coil is going to make that field, and that field is going to destroy that switch, not this switch. Okay? So if we put a diode, there's a polarity now, and you can only connect this in one way. This one would have to be the positive, and this one would have to be the negative, because the diode arrow on the schematic will point to positive. So there's another clue. If I don't have any really, neat color codes, and this is just like wire, LF21, and this is wire LF22, and this is wire, LF23, okay, and that's all I see. Well, the fact that this is pointing to this wire, then that means this is the positive side. Okay? So there's another little clue. So what you have to worry about is this. If this diode fails in the open position, meaning it just stops being a diode and it's just a broken wire basically, or if it breaks, which I've seen, then this switch here will be destroyed. If this diode shorts, meaning the current just flows straight through it, this fuse right here will blow, because think about it. If this is just a straight wire, the electrons don't have to stop here. They boom, boom, blow the fuse. Okay? So, review. Our expression, electromagnetic conducting, a coil of any kind produces a magnetic field that when it collapses produces a voltage according to Lenz's law, and that voltage will tend to make current continue moving in the same direction as the current that originally made the magnetic field.